Okay, so with that all out of the way, let's talk more about graphs. So first, I hope you're having a wonderful day. So we first talked last day about what a graph is, and we talked about how graphs can be used to model all sorts of different things. We talked about the computer network, we talked about how I could have a flight map where I could have different airports and I could travel between them, or I could think of it like my favorite park I want to go for a walk in. We talked about a lot of different terminology about graphs last day. I'm going to be doing a bit more of that today, but I'm going to present you some interesting properties that some things involving graphs actually do have. So I want to talk a bit about degrees, and I'm not talking about academic degrees. I'm talking about degrees of vertices. So let's talk about degrees and the handshaking lemma. So I need to define what a degree of a vertex is. So let me define that here for you. So let me draw you a picture. This makes things a little easier for me to define, and then I'll write it out for you. So I'm going to use the same graph I used last day, except I'm going to use the undirected version that I initially had. C, F, and E. This fun picture I kind of cooked up here. Did I ever mention that you could draw some pretty neat pictures with graphs? But this isn't really one of the ones I would point at and say that, but it's kind of cute looking. One thing I do have to make a remark about is that different graphs actually have different meanings for which, depending on their connectivity. So for example, I could draw this graph many different ways. For example, I could have drawn that E over here. I could have put the F like way down here. They don't really have any geometric meaning more generally. However, some people can impose restrictions on the graphs, or they may be interested in problems that involve, hey, look, I want to draw the graph that has this certain property. People do study things such as this, but I feel like I need to make sure I mention that at some point, and that's when I'm saying it right here. So, for example, if people impose a geometric meaning to the graph, they may, for example, have like those weights that I had last day about distances, they may actually physically enforce that on the graph itself so that it matches what it should be in a physical sense. But that really isn't about degrees. I just felt like mentioning that because I always have so many things I want to talk about with graphs. So I want some way that I can talk about the number of endpoints. So say if I give you a vertex A, I would like to have some way to talk about the number of neighbors it has. So for example, if I look at vertex A, I want to know, okay, well, how many neighbors does A have? Well, it has B, C, F, and E. A neighbor simply is a vertex that it's adjacent to. Another way you can also view this is that there's an edge that's incident on A, and you look at the endpoint and you ask, okay, well, are they adjacent? Well, how many do I have here? I got 1, 2, 3, 4. I have 4 neighbors for A. This is one way we can talk about the degree of a vertex, but I'm going to define it more generally just to make things a little easier for us. So here's the degree of a vertex. So I'm going to talk about in an undirected graph. In an undirected graph, the degree of a vertex V which I'll denote, so I'll say denoted deg of V, like this. That's how I'm usually going to denote the degree of a vertex V, is the number of incident edges. It's the number of incident edges on or of V, wherever way you would like to phrase this. So if I look at all of the incident edges, so this is another way you could think about this, is if I look at all the edges that are incident on A, so this one, this one, this one, and this one, I want to know how many edges there are incident on this vertex. So for example, if I look at the degree of A. Degree of A is equal to 4. How about the degree of C? Can somebody tell me what the degree of C is? What's the degree of C? It's 2, exactly. Very good, very good. How about the degree of E? What's the degree of E? 1. See, like I said, you guys are all pros at this. Awesome. So let's, so I do want to make one remark. This is more of a convention, but there's a way you can interpret this. Is that I'm going to say, note that a self loop. So remember, I talked about those near the end of last day. Those are those loops I put where the endpoints are both the same vertex. Note that a self loop adds 2 to the degree. So this is, some people in the graph theory community will say this is a fine convention to use. Some people will say, it doesn't really matter. I'll usually stick to this. There's a reason why that I will be alluding to in a bit. But anyways, so that's the notion of degree. Is everybody okay with this definition of a degree? So it's just the number of incident edges on a vertex. So I just count the number of edges that are incident on a vertex. So this is A here. I just count all of those little sticks connecting off of it. That's all it is. So that's one notion of degree. There's also this other notion called an in degree and an out degree. So if you talk about directed graphs, there's the notion of in degree. So in a digraph or directed graph, I'll just say digraph. The in degree of a vertex V, which I'm going to denote as dag with a minus sign just above it, like this, of V, is the number of incoming edges to V. So remember I talked about how edges, they go from one endpoint to another. So when I talk about the incoming edges, that means the arrows that are pointing in towards a vertex. Hence why we call it in degree. So if I give you a directed graph, if I have a whole bunch of directed edges pointing towards that vertex, each one of those arrows pointing at the vertex adds 1 to the in degree. You can also analogously define the out degree. So we're going to focus primarily on just degree, but I feel like I need to mention these. Is that, so in a digraph, so it's the exact same beginning of this, just I'm kind of running out of space here. The out degree of V, denoted dag with the plus instead of a minus. Dag plus V is the number of, you might guess it right away, it's going to be the number of outgoing edges, right? Is the number of outgoing edges from V. So remember, we have edges that go from a vertex to another one. I'm just counting all the arrows that splay out from a vertex. So for example, imagine if I considered, say, this mix, like say if I added 2 directed edges like this, don't worry, I'm not going to be using this example a whole lot. But I just want to point it out. So notice if there's 2 arrows leaving out of here, that means that the out degree of this vertex, say B, was in fact 2. But if it was the case that 2 were pointing in, I would say that the in degree is 2. However, notice that because there's no incoming arrows, then I could say that means that if there's no arrows pointing at it, that means, of course, that the in degree is, what would it be? If the out degree is 2, then that means the in degree, the arrows that are pointing in towards it, that's 0, right? But I'll let you think about these bottom two here. I want to focus primarily on the definition of degree. So let me proceed to what is a very classic result that's very cute and very easy to prove. It's often referred to as the handshaking lemma or the degree sum formula. Some people like I said, this result is very cute. It's so simple to prove that a lot of people like to give it different names just because of how cute and applicable it can be in many different circumstances. I call it the handshaking lemma because that's usually how the proof all goes. But let me describe this for you. For any undirected graph, now when I say any, I literally mean any. Just to be very clear, for any undirected graph, so last day I said, oh, make it, I'm not making any assumptions, other than, oh yeah, it's simple, it's undirected. I'm literally saying any undirected graph. That means that this graph may not necessarily be simple, so that means it may have multi-edges and self-loops. For any undirected graph, G is equal to VE, the following property is true. The sum over all the vertices. So I'm going to take each one of the vertices. I'm going to examine its degree. So for each vertex in the set of vertices, I'm going to sum or contribute to a sum its degree. This is going to be exactly equal to 2 times the number of edges. Remember, M is the number of edges. That's the way we defined it last day. So you might ask, Dan, this seems rather interesting because now you have some relationship between the degrees of the vertices and the number of edges. Now, you might say, Dan, how do you get this? How do you know this? The hint is really the name of this lemma. And I'll tell you how you prove it because it's really that simple. It's probably one of the easiest kind of counting arguments I could think of from graph theory, but it's also equally quite applicable. So the reason why we call it the handshaking lemma is because imagine you have a series of handshakes that can occur. Say, I'm going to have a handshake with somebody else, I'd say at a party. And I want to say, hey, look, nice to meet you. And I shake hands with them, and they may shake hands with me. So there's generally this question of, okay, well, if I ask me how many handshakes I made during this entire ruse of going around to this party, and I ask everybody else how many handshakes they've made, it's actually going to be equal to twice the number of edges. And here's basically how it works. You use double counting as the argument here. So watch this. By definition, the degree of V is the number of edges incident on a vertex V in obviously our set of vertices. Now, there's a very interesting thing we know about every one of our edges. Well, every edge is incident on 2 vertices. I'll make a remark about that after I finish writing this down. So remember, every edge is incident on 2 vertices. On 2 vertices. So by double counting, every edge is counted twice, in the sum by sum of my degrees. That's really it. That's it. So all I do is I look at each edge and I say, okay, well, from the perspective of one of the endpoints, what happens? Well, if you imagine like my handshake, when I count my handshake, it's one endpoint in an edge. When I shake my friend's hand, I shake hands from the perspective of that person, it's like me at contributing to the total number of handshakes from each other's perspective. But each one of those, the true handshake, the true count of how many handshakes happens, is each edge, right? But what happens? Well, from everybody else's perspective, they shook somebody's hand, meaning that each edge contributes twice to the number of perceived handshakes. And that's why you get the double counting occurring. So question, what is V in V? Okay, so if you're wondering about this, so this is to be clear, this means in. So for each vertex, so this is each vertex V. And of course, this is in. And V right here, this is your set of vertices. So all I'm doing is I'm plucking out each vertex from the set of vertices, and then I examine the degree it has. Now, if you're really thinking about this carefully, if you look at my proof, and I said that this works for any undirected graph, right? You notice that I didn't really say anything about loops. Did you notice that? Did anybody notice that? That I said nothing about loops in this? But there's something very slick about what I did a moment ago that allows this proof to work. Does anybody remember how I defined the degree of a self-loop? Or a loop, whatever you'd like to call it. I usually call them one or the other. So its degree was what? So if I give you some self-loop on a graph, how much does it contribute to the degree of a vertex? It's 2, right? So as far as the loop is concerned, I have 2 vertices, but each one of them will contribute 1 to the degree. So this proof is perfectly fine. In fact, this works, like I said, for any undirected graph. So it doesn't have to be a simple graph. It could be a multi-graph. Very interesting, right? So we're going to use this. You might ask, Dan, why do we need to study this thing? It's because we're going to use it when we talk about a particular version of how we represent a graph later. But I don't want to tease too much about it. We're going to use this fact oftentimes to make counting arguments. I also do want to make a remark that there is also a version of this theorem for directed graphs. For any digraph. For any digraph, G is equal to VE. You can take the sum of all of the in degrees and all the sum of the out degrees. You can compare them and you actually find out, hey, look, they're actually equal to one another, and they in fact equal the number of edges. So if I take the sum of all the vertices, sum over all the vertices, I take all of the in degrees. This is actually equal to the sum when I sum over all of the out degrees. And this is in fact equal to the number of edges. You might ask, Dan, why is that the case? I'm not going to write out the proof here, but the argument is very similar. So notice that every time I contribute an edge that points outwards, that means that there has to be another vertex where that arrow is pointing towards it. Does everybody see that? So whenever I take a vertex, and say I have a directed edge that goes like this. From this vertex perspective, I'm contributing to the out degree, right? I add 1 to it. So the out degree goes up by 1 here. But notice here that when it points at this vertex, now it's actually increasing the in degree by 1. So every time you have an arc that goes from one vertex to another, you're always going to have this balancing effect that happens. And that's how you count to achieve these sums. Is that interesting? So these are good examples of so-called combinatorial arguments. You can do all sorts of fun things with counting when you use these types of arguments. But are there any questions about the handshaking lemma? This is a very cute result. Every once in a blue moon, it does creep up in things that we do. So it's something that you should get familiar with knowing about. Are we all good? Give me a thumbs up. Give me a thumbs up. Okay, great. So now I want to switch gears. I'm going to talk a bit more about different structures that graphs can have. Wonderful, wonderful. Okay, so let's talk a bit about complete graphs, because I want to make sure we have some similar terminology we're working with. Let's talk about complete graphs. So let me define this for you. A complete graph on n vertices, which I'll denote. So denoted with a capital K with a subscript n. I'll usually call it Kn. Is an undirected graph. It's an undirected graph where every vertex is adjacent to every other vertex. Every other vertex. Kind of cute, right? So sometimes it makes it handy to define things on complete graphs, because then you have this property you can work with. So just as an example, I'm going to draw you some fun pictures. So here's an example. Here's K1. I'm not going to worry so much about labeling any of these vertices. So that's K1. Notice it's just one vertex. There's no other vertices, so there's no other edges. K2. So notice there's two vertices. I just introduced an edge, and now every edge is adjacent to every vertex is adjacent to every other vertex. K3. K3 is really interesting because it's just a triangle. And oftentimes people will refer to this as a triangle. So if anybody asks you, okay, what's a triangle graph? They'll tell you that's a triangle. It makes sense. It makes sense, right? But remember, it doesn't have to literally be a triangle. That's what we call it in graph theory. And now here's one that's kind of neat. So here's K4. There's an interesting way you can draw K4. There's a lot of different ways you can draw K4. Here's K4 right there. So notice every vertex is adjacent to every other vertex. I like it because it's kind of neat, because now it looks like it looks so pretty, doesn't it? So now I can take, for any n, I can basically describe to you how I build the complete graph. So effectively, if you wanted to give me Kn, imagine I have n vertices. Let's say I'll start off with these 5 here, and then I'll imagine I have an nth vertex. I'm going to start connecting vertices so that they're adjacent to each other. So I'm just going to kind of take a little stroll where I'm going to put every one of these adjacent to one another. So I'm just going to kind of take a little walk around this whole thing. So I'm just going to, so everywhere I don't have an edge yet, I'll make sure I include one. Whoops. As if I can't do straight lines today for some reason. And then we got 5 here. There may be more. There may be a whole bunch more over here. And then ultimately, you're going to have Vn connecting to all of these. So there may be more vertices and more edges. So I'm just connecting all the vertices to each other so that every vertex is adjacent to every other vertex. So this would be effectively how you'd construct Kn, if you find yourself curious about it. And I want to ask you a question. How many edges does Kn have? Does anyone have any ideas? How many edges would the complete graph have? And choose 2. That's a pretty specific guess. I like that one. I like that one. I like that one. That's very good. Very good. Very good. Very good. So I'm going to derive it in a simpler way so that you can see it quite quickly. Wonderful, wonderful. So notice that for each I is equal to 1, 2, all the way up to n, vertex vi is adjacent to n minus 1 other vertices. Now the interesting thing is that we technically double count the edges. This is where things are going to get a little weird, but it's really not that bad. But we're going to accidentally double count the edges. We double count the edges. So first, to just be clear what I mean by double counting, it means I'm over counting in this case. So every time I say, okay, vertex vi is adjacent to n minus 1 other vertices. Okay, so when I look at this one, okay, I see n minus 1 vertices, right? When I look at this one next, you would agree with me that now every single time I do this, I might be technically counting more edges that I already counted before. So notice that this edge I already accounted for when I looked at v1, right? Just as an example. Same idea with v3, each one of those. I'm going to actually count each edge twice. So it must be, I don't like using the word must, but I'm doing it today because it feels like fun. It must be that m, so the number of edges, is n, because remember, I'm considering n vertices, and each one of them has n minus 1 other vertices, they're neighbors to. And since I double counted them, I half that. So that's how I can derive this bound. So that means that if you're thinking about this, think about this for one moment. The reason why I want to show you about complete graphs is that complete graphs have the largest number of edges possible in a simple graph. So if I give you a simple graph, remember they don't have multi-edges or the loops. That simply means that, hey, look, there's not going to be more. You can't have more than putting every edge so that every vertex is adjacent to every other vertex. So what does that mean? That the max number of edges in a simple undirected graph is m, which is going to be at most this, which let's talk about in terms of big O. What's that in big O? Which is big O of what? N squared, perfect. Now, you can also derive the same argument with directed graphs, but you won't have this double counting issue. Because remember the last day I talked about how you can replace any undirected edge with two directed edges? So like I could take each one of these and I could say, okay, there's two directed edges for each one of these original edges. So this double counting actually doesn't happen there. So for directed graphs, you don't have the divided by 2, but you still end up having a quadratic number of vertices, largest possible in relation to the number of edges. So this serves as a nice asymptotic upper bound on the number of edges for any simple graph. So that being said, when we come back, we'll talk more about more structures involving graphs, and then we'll be talking about how we can represent graphs on computers. So that being said, I want to say thank you very much and have yourself a wonderful weekend. I'll see you later.